Okay, welcome to this video for Chem 161, where we'll look at the final category for covalent compounds. So covalent molecules involving homonuclear diatomic, so for short, diatomic molecules. Homonuclear indicating the same type of element, diatomic meaning a dimer of that. And we'll look at some practice with our naming from all the other class of compounds that we've studied, covalent compounds and ionic compounds. So we'll sort of look at some practice here. Okay, so just to cover this last class of molecules, there are a certain set of elements from the periodic table, namely hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. These ones here, these elements are never found. So H, N, O, F, Cl, Br, and I. These ones are never found alone or in their single atom state, and rather they bond with themselves or to another element. Okay, so this would be electron sharing. So we're going to call these diatomic molecules that result, we're going to call them covalent bonds. And so we'll see that they are therefore expected to be dimers of what we have there. And so we expect to never find hydrogen by itself, but instead always find it as H2. Likewise for nitrogen, N2. Oxygen, O2. Fluorine, always found as F2, chlorine, Cl2, bromine, Br2, and iodine, I2. Okay, so thus the diatomic nature, you see the dimer of those. And there are ways to remember this. I think I've previously indicated that we could remember Brinkelhoff. Is one way to indicate bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine are those elements. Some people also use a saying like, never fear ice cold beer, and the acronym of that would indicate the first letter of these elements. So this is a way to remember that this class of covalent diatomic molecules comes from dimers of these elements. Okay. So with that, we should be able to move forward and practice some naming based on either being provided with the formula or being provided with the name, be able to identify the type of bonding present so that we can apply the right rules for naming, and likewise identify the type of bonding present to determine the formula as needed. Okay, so this might be a point where you recreate this table on your own worksheet and attempt these exercises on your own, and then resume the video to check your work. Okay, so in the first option, we're dealing with Fe parentheses NO3 close parentheses 3. So we have to identify whether or not we have ionic bonding or covalent bonding. And in this case, I'm automatically putting my eye at the iron, so that is clearly a metal. And then the latter half of the formula, I see a polyatomic, NO3. I recognize that as nitrate, and I see 3 of those. So this is indicating to me that we have ionic bonding present in this compound. So we kind of start with that. I am then allowed to apply the right naming rules on this one. and we can kind of move forward. So looking at the first part, we've already memorized the nitrates, so this helps us recognize that we're dealing with NO3, and the charge on this was -1. Okay, so NO3 minus was something we've memorized. That is nitrate. And having memorized that, we can see that the 3 on the parentheses at the lower subscript position must be a charge due to the iron. So we must be dealing with an Fe3+, which is providing the subscripts on the position there and there. Okay, so with that, I think we're ready to name the compound. We see iron is in the D block. It's in that transition metal area, so we're going to have to apply a Roman numeral to list the exact type of iron we're dealing with. Okay, so we're dealing with iron Roman numeral 3, and we've memorized and recognized the nitrate there for the anion. So ionic compound, ionic naming rules, and we've applied the Roman numeral because we're dealing with a transition metal there. Okay, in the next category, we first draw our eye to the name, of course, here, and so I see lead for sulfate. Sulfate is an anion that I've memorized from my polyatomics list, and lead, I see the Roman numeral, so this must indicate that lead is a transition metal, and we look for that, and that's going to be element Pb from our periodic table, and we're seeing that here. Okay, so in this case, we're going to apply ionic naming rules because this is an ionic compound again, the lead being on the metal side of the periodic table and the sulfate being our polyatomic ion. So because we're dealing with an ion by default there, we must have ionic bonding. Okay, so with that, we can kind of look at what we know about this. It looks like lead, we're dealing with a symbol Pb. The 4 is telling us that we are 4+, and we've recognized sulfate as SO4 SO4 2- from our previous exercise of memorizing. And so now we're ready to build the formula out of that. Okay, so we're going to list Pb, SO4, and we're going to consider what's needed for subscripts to balance charge. So remember, we can consider as a starting point the cross lowering exercise. So we would have 2 for the lead and 4 for the sulfate in parentheses. Now that can be simplified further, and so I'm expecting to need some parentheses here on the sulfate. Okay, so SO4, I'm going to put parentheses there, and as a first iteration, I'd have a subscript 2 on the lead and a 4 on the sulfate, but that can obviously simplify to lead 1, sulfate 2. So that is the formula for our lead sulfate compound here. Okay. Some of you may have recognized that lead here isn't in the transition metals, and as we get deep in the periodic table, some elements here can adopt different oxidation states or different charge values. We're seeing that indicated with the lead 4 option. Lead 2, for example, is also known, so we're indicating here and applying some rules outside of the transition metals, and this is sort of an exception as we're deep in the periodic table. Very heavy element here in lead. Okay, moving on, we've got the next row, so N2O5. We look to identify those elements. We're dealing nitrogen and oxygen, so they're in column 5 and 6 of the main group area, the P block. 2 nonmetals are there, so we must be dealing with covalent bonding here. So now I'm reaching into my memories, and I'm going to apply covalent naming here to identify the name here properly. Okay, we have nitrogen, so we're going to apply the first word is going to be nitrogen, the full element name of nitrogen, and I'm going to indicate a prefix should the number of nitrogens be greater than 1, which it is. So I need to use dinitrogen, and now I need to remember how to indicate the 5 on the oxygen piece here, so I'm going to apply penta and oxide. Okay, pentaoxide. Okay, here's an awkward moment where we have two vowels next to each other. Pentoxide would be accepted in certain circumstances, and I believe pentaoxide is what's accepted on your SmartWorks. So do let me know if there's a discrepancy there, but pentaoxide is what you typically see most prevalent in the literature there. Pentaoxide. Notice we've adopted the first part of the element name, oxygen, and added the "ide" as a suffix on that second word to indicate that oxygen is the second element in this covalent compound. Okay, next one, ammonium chloride. So hopefully we recognize the ammonium. So this is NH4. Remembering the charges might be the hardest part here. So that's NH4 plus. We see chloride. So we notice the suffix "ide." We remove that and we add the end of the element name to identify chlorine. So we're dealing with the anion of chlorine. So this is Cl minus, given that chlorine is in the 7th column of the main group area of the periodic table. And so we've got a charge value of -1. We've memorized NH4 to be plus 1 in this case. So clearly we're dealing with ions, so this is ionic bonding present. And we can now piece together the formula. So NH4 was the cation. We always list cations first. And Cl is the second. So ammonium chloride. Parentheses are not needed since we have a 1-to-1 balance of the polyatomic, that is the ammonium, and a 1 chloride to balance that charge with a single minus value there. Okay, so that's our formula for that one. All right, moving on. We're given LiI, capital I, so two elements here. We recognize lithium and we recognize iodine. Okay, so lithium is from the alkaline metals, group 1, and iodine is group 7, so we're across the boundary there. So we've got a metal and a non-metal. This must be ionic bonding. Ionic compound rules are going to kick in at this point. List the element name for the first cation, for the first species there, so that is lithium. All right, followed by a modified version of the anion that is iodine based, but we have to apply an "ide" as the suffix, so iodide for that. Roman numerals are not needed because lithium is not in the transition metal area of the periodic table. Okay, next one, trinitrogen diphosphide. So here we're dealing with nitrogen right here, and we're also dealing with phosphorus right below it. So two nonmetals. This is a covalent compound with covalent bonding. Okay, with that we can now build up the formula here. So I see nitrogen, the full element name there, so I can write an N. I see the prefix of 3. I can apply a 3 directly to that. Phosphide. So now this might be the hard part. We have to recognize and distinguish this from other P-type anions that we may have seen in our work thus far. So be careful to distinguish this from phosphate as an example and other P-type elements. So phosphide, if we remove the "ide" and look for the remainder on the periodic table, we'll see that we are dealing with phosphorus here as an element in this covalent compound. Okay, so diphosphide is going to mean that we have phosphorus P, not potassium. Be careful with that one again. And we're going to have a subscript 2 there given the di prefix on that second word. Okay, moving down, we've got AgBr. Okay, so we're looking to identify if that's ionic or covalent. We have Ag in here, and we have bromide over in the 7th column, and so we are dealing with a metal and a non-metal, so this is ionic bonding. We also recognize that here the silver is definitely in the transition metal area, so we might otherwise reflex and think about Roman numerals. However, hopefully you've recognized that silver is one of our exceptions. It only has one charge option for its cation. It is always and only +1. So we know we are working with silver +1 just by seeing the Ag species here in the formula name. never any other options. So no Roman numerals needed here. Bromide, of course, is always Br minus, given that it's in the 7th column of the periodic table of that P block area. So always goes to 7 minus 8 minus 1 in charge. So this compound is going to be called silver brome. And now we have to remove the ending of the element name for the ion of bromine and apply the suffix "ide." Silver bromide. So no Roman numerals needed on that exception there. Okay, moving down, we're now given the name ammonium phosphate. So we've worked with ammonium before, and we recognize that as NH4+. And the phosphate, we worked hard to distinguish that from phosphide above. Phosphate is one that we recognize, and this is PO4 3-. Okay, phosphate, PO4 3-, one of the polyatomic ions we've had to memorize. Okay, and we can think about our kind of cross-drop trick to predict a starting point for the subscripts here. So we'll be looking at phosphate with a 1 and ammonium with a 3 and considering simplification thereafter. The 1 is as low as it can be, so we can't do any simplification thereafter. We just have to carefully position some parentheses on this one to show that the 3 from the phosphate is in that minus charge. We need 3 of the NH4 entities to charge balance that. Okay, so we're going to list the NH4 cation first. I'm going to need 3 of those to give an overall 3+ so far in our formula, and that is sufficient to balance the rest of the formula, which is the other polyatomic ion of phosphate, and we have that listed in completion there with PO4. Okay. Of course, we were dealing with polyatomic ions there, so this is ionic bonding there. Okay, and on our last example here on our chart here for our video today, we are working with N2F4. Okay, so nitrogen, 5th column, fluorine, 7th column, clearly across the metalloids staircase boundary, non-metal, so we are dealing with covalent compounds. In this case, covalent bonding. 2 nitrogens is indicated with the N2, so we must apply dinitrogen. And then the 4 fluorines is going to demand its own prefix, so we will be working with tetra to indicate that 4. And rather than listing fluorine, we will list list difluoride here. Okay, so we will apply that suffix of IDE here, dinitrogen tetrafluoride. Okay, and that's all of our examples there. So hopefully that's been good practice for you.